Okay, so hello, my name's Jamie and I'm a PhD student at the University of Bristol. My work focuses on the use of tufting within sandwich structures, and today I'm going to talk a bit about my current work on observing the process parameters within these types of structures. So first of all, what am I going to talk about? Well, this project has its background within the automotive industry, so I'm going to talk a little bit about that first and its use in crashworthiness. I then go on to introduce tufting, before I introduce the experimental testing that I've been carrying out and results and conclusions of that. So first of all, as I said, some background in the automotive industry. So the automotive industry itself is looking more and more into the use of composites to reduce the weight of the vehicles. This is because of the stricter regulations on fuel emissions and fuel consumption, and so forth. There's a renewed interest in battery-powered vehicles and hybrid vehicles, and these require significant weight reductions to be able to meet customer demands. Now, one of the key design issues that comes with composite materials, as opposed to the cost and the manufacturability of them, is their use within crashworthiness within a vehicle. In particular, side impact of vehicles is particularly important to design for because of the reduced area that you have to absorb the energy of the crash, but you must also be able to protect the occupants, and as is more the case these days, the battery itself as well. So composite sandwich structures are a potential use in automotive industry because of their high stiffness and relatively low weight, but they need to be able to absorb large amounts of energy in a crash. As you can see on the left here, one of the issues of an edgewise compression of a sandwich structure is it will tend to disbond from the core and fracture and delaminate quite significantly. Now what you can see here on the right is a test carried out in conjunction between the University of Bristol, the University of Delft, and BMW, where they've used tufting as a form of through-thickness reinforcement to increase the energy absorbed during an impact event. And as you can see here, the damaged site is significantly smaller. And this resulted in almost a doubling of the amount of energy absorbed in the crash. So what is tufting? So tufting is effectively a form of stitching method using a single needle and the threads not going in under any tension. So what I've got here is a video that will hopefully show a bit clearer as to how the process works. So it's carried out within a dry preform, and the needle simply slides in and out through the same point, leaving the thread behind through the friction of the preform. On the back surface, you can see that there's a small amount of material left behind, and this will form a loop on the surface, which I will come to on the next slide. And then this preform is then infused with resin to saturate the part before it's cured. So, as I said before, these loops are formed on the back face of the part after infusion, but as you can see here, there's quite a significant amount of variation left behind after it's been cured. For example, some of the loops are missing, where it shows the tuft has not completely gone through, or there's significant variation in the loop size. So the idea of this research was to find out what impact this would have on the structural behavior of the part when it's in service. So the idea was to develop a mechanical testing technique that was able to capture the performance of individual tufts and identify the failure mechanisms of these, and therefore find out the impact that variations of the tuft formation would have on that. So the actual robot tufting process at the NCC allows us to control the length of the tuft, and through the use of this we were able to explore various different parameters and their possible effects. So what you can see along the bottom are several images of different tufts captured through their cross-section. So on the far left you can see what a single tuft would look like normally. This second image here shows the effect of removing the thread before infusion, which therefore leaves behind a resin column. The third image from the left shows what would happen if you pass the needle through the same position multiple times and therefore leaves multiple tufts behind. And the image on the far right is showing the effect of the needle not going all the way through the preform and therefore leaving behind a partial tuft. So, as I said, the idea was to come up with a mechanical test that was able to capture the impact of these individual tufts. Now currently there's no test standard available for something that focuses on an individual through-thickness reinforcement, and therefore a new design was required. So this here is a summary of the geometry of the test coupon that was used. It's based around the unit cell of the tufted materials. So in the top area here, you can see what is effectively the gauge area with the tuft located in the middle. And this spacing was chosen based on previously tufted panels and the tuft spacing that was used for those. At the top is a crush trigger. Effectively, this is to create a stress concentration that allows for progressive crushing to continue from this point. And the large base area at the bottom is used for clamping of the coupon during the test. So, and you can see on the right here is showing where the tuft is located in the real test coupon and how that corresponds to the gauge area on the left. So the actual test procedure was carried out in the labs at the University of Bristol. It's carried out as a very slow loading rate of quasi-static of 2 millimeters per minute, which is basically being used to validate this process before it would ever be carried out as a dynamic test, which is obviously more suited to the automotive industry. So what I'm now going to show is a quick summary of some of the experimental results. You can see that in the graph on the top left, the effect or the difference between a typical tufted coupon and one which is untufted, so the baseline sample. And you can see that there's quite a significant difference between the green and the red line at the point where the tuft is carrying the load, and therefore it's showing the actual benefit of the tuft. Along the bottom shows 3 images that are capturing the various stages of the test. So in the bottom left you can see the initial fracture within the trigger region. The central image is showing the progression of the folding of the skins and disbond between the skin and the core around the tuft. And finally, the final image is showing how this folding motion has continued and the core area around the tuft has started to disappear after the tuft has failed. So as I said, there's a significant increase in the load between the tufted and the baseline, and what this is showing is that this test is successfully capturing the effect of the tuft within the sandwich structure. So what I'm now going to do is summarize some of the parameter comparisons that I carried out and how the results compare between them. So first of all, we'll start off with a baseline test, as we saw before. Now what we can start to see is with the addition of various components of the tuft, beginning with the resin column, we can start to see the changing effect of the load. So if we now go into the partial tuft, again we see a small increase in the load before we start to see the effect of adding tufts that have penetrated all the way through, and we're now starting to vary the loop size of these. As you can see, as we increase the loop size, these lines are clustering closer and closer together. Now, if we take those away and go back to just a single tufted specimen over the baseline, and we start to add in the effect of multiple tufts, we start to see that the load is gradually increasing more significantly. So finally, bringing all of those together, what does it show? Well, first of all, the lines that are showing various loop sizes within the tuft region, it's very hard to distinguish any significant differences here, which is implying that the tuft loop size is having very little effect on the actual loading behavior. Whereas the two that were carried out with multiple tufts have increased the load even greater over the baseline, and therefore this is implying that this is more significant than the loop size. So I'm now going to have a look more closely at how these coupons are failing and why the effect of this could be. So as you can see on the left-hand side, this is a side view of one of the specimens after failure. And you can see there's a significant number of failure modes occurring here, including delamination of the skins, a disbond between the skin and the core, and then also folding of the skins. And then on the right-hand side, you can see the top view. What you can see here are these 2 yellow regions where the tuft has been left behind. But what is not clear is how this tuft is actually failing, to therefore try and correspond that to the loading results. So what we're able to do is, by dissolving the ROSL core of the sandwich within a sodium hydroxide solution, we're able to isolate the tuft column, and therefore what we can see is how this tuft has started to fail. So as I said at the bottom, there's a combination of thread pull-through and thread and skin fracture, which is implying that the tuft is failing more in a shearing motion as it's being pushed down rather than a tensile failure and pull-through of the loop. So just to sum up with some conclusions, so a single tuft test method has been developed to investigate the effect of the tuft formation on its crushing behavior. We've seen an increase in the load between the tufted sample and the untufted baseline, which is in some way validating the test by showing it can capture the tuft. And then the 2 main conclusions of the results showed that increasing the amount of through-thickness reinforcement had a much more positive impact on the crushing performance than varying the loop size, and this is probably because of the less expected failure mode of shear rather than a tensile failure of the loop. However, this is an encouraging sign for the process robustness, because it shows that variations as a result of the manufacturing process are not going to have a significant effect on the test. So I'd just like to thank the EPSRC for funding this research, Harry Clegg and Paul Barrett at the NCC and University of Bristol respectively for helping with the manufacture, the NCC for time on the Tufting robot, and for BMW for supplying the materials used. Thank you.